When a block slides across a rough surface, it experiences a frictional force opposing the motion. Similarly, when a fluid flows past a stationary surface, it experiences a force opposing the flow. This tendency to resist flow is called a viscosity. Fluids like air have low viscosities. Thicker fluids like water have high viscosities.
Take a fluid in a tube because adjacent portions of the fluid flow past one another with different speeds. A force must be there in order for a fluid to maintain the flow. In an ideal fluid, which is an assumption that fluids flow without frictional losses and that the molecules in a fluid have no interaction with one another, flows through a tube with a speed that is the same everywhere else in the fluid. In a fluid with viscosity, the speed of the fluid goes to zero on the walls of the tube as it reaches maximum value in the center of the tube. The force causing the fluid with viscosity to flow is provided by the pressure difference across the length.
The required pressure difference depends on four factors, which are the average speed of the fluid, the length of the tube, the cross-sectional area of the tube, and the coefficient of the viscosity of the liquid. The formula is P1 minus P2 equals 8 pi eta times V times L divided by A. P1 minus P2 is the pressure difference, eta is the coefficient of viscosity, which is the constant of proportionality between the pressure difference, and V times L divided by A is where V is the average speed, A is the cross-sectional area of the tube.
The volume flow rate is an efficient way to characterize the flow of a fluid. The volume flow rate is the volume of fluid that passes a point in an amount of time. The formula is V times A, where V is the average speed of the fluid and A is the cross-sectional area of the tube through which it flows. Substituting a value for V, which is P1 minus P2 times A divided by 8 pi NL, will give us a formula of P1 minus P2 squared times A divided by 8 pi NL. Jean-Louis Marie Poiseuille, a French physician and physiologist, formulated this mathematical expression for the flow rate for the flow of fluids in circular tubes. This is known as Poiseuille's law.
During his lifetime, Poiseuille's law was only modestly recognized. In 1835, the Academy of Sciences awarded him half of the prize for experimental physiology. In 1845, he won the prize for medicine and surgery, and in 1860, he received an honorable mention, again from the Academy of Sciences. Although Poiseuille was an elected member of the Paris Academy of Medicine, his numerous attempts to win election to the Academy of Sciences were never successful.
We did an experiment that showed viscosity through the use of shampoo in a bottle that is heated and cooled. For the experiment, the materials required were a large bottle of shampoo, clear plastic bottle, stopwatch, marble, pen, both hot and cold water, ruler, safety goggles, ice cubes, paper towels, a container, and a thermometer. First, we drew two lines all the way around on a bottle with a pen. Then, with the ruler, we measured the distance between the lines. After you uncap the bottle, insert a marble in the bottle and turn the bottle over. Turn the bottle over once again and using a stopwatch, measure the time it takes for the marble to travel from top to bottom. Next, we investigated the viscosity of shampoo at a warmer temperature. We filled a bowl with warm water and let the shampoo bottle sit in the bowl for approximately 15 minutes. We rotated the bottle so the heat can evenly distribute throughout the bottle. Then, we calculated the time it takes for the marble to travel from the top line to the bottom line. We also investigated the viscosity of shampoo at a colder temperature and measured the time for the marble to sink in the bottle.
We measured the time it took for the marble to sink from the top to the bottom of the shampoo at 3 different temperatures.
The time for the marble to sink in shampoo at room temperature was greater than the time to sink the marble in warm shampoo and less than the time to sink in cold shampoo. From the data, we see that cold shampoo has a higher viscosity than warm shampoo and shampoo at room temperature. Thus we can infer that the viscosity of shampoo increases as the temperature decreases.
There are many implications of viscosity. One example is brake fluid. Brake fluid transmits force to the braking system and it would not operate properly if it had a different viscosity. Lubricants from many machine systems also work the way they do as in part of a result of their viscosity. Suntan lotion could not be spread across the skin if it didn't have viscosity, because it would drip all over your face before you could start rubbing it in. Thus, many cosmetic products depend on viscosity to be able to be applied properly.
The motion of the falling raindrops is opposed by the viscous force offered by the air. Hence, raindrops fall slowly. When the arteries and veins of the human body contract, their sizes decrease. Hence, the flow of the blood is affected due to the viscosity of the blood, and the blood pressure increases. This affects the functioning of the heart. When the temperature of a human body increases during fever, the coefficient of viscosity of the blood decreases. This increases the blood circulation, and the normal heart functioning is maintained.
The viscosity is very important in our daily lives because it determines how the substance should be handled, stored, and discarded. Fluids are all around us, and the behaviors are significant to our daily lives, sometimes even survival.